Hi 13 diplomas and welcome back to 18.2 Part B. So we were just talking about before about writing equilibrium expressions for weak acids and weak bases. So we know that a weak acid is one that partially dissociates and that most of it actually remains intact as the acid, okay, and there's very few ions, okay, so that's a generally what happens. So we can work out the equilibrium constant to actually tell us what degree of an acid does it dissociate. So how strong is that weak acid essentially. Now just to give you a bit, I made up these values just to give you a bit of a concept. If we had a concentration of 0.1 mole per litre of ethanoic acid, very little of that ethanoic acid would actually dissociate. So you'd end up with about 0.001 of hydronium ions and 0.001 of ethanoate ions. And so I made these values up. It's just to show you that actually if this is how much acid you've got, very little of it breaks apart. So somebody has been amazing and gone and worked out all of the equilibrium constants for all of our weak acids and bases. And so we can just look them up in a data booklet, like your resource booklet for your exam. And the equilibrium constant for ethanoic acid is 1.74 times 10 to the negative 5. And remember, to do an equilibrium constant, it's products divided by reactants, but we ignore the liquid water because its concentration doesn't change. Now this Ka will be its Ka unless the temperature changes. So this is just its Ka at 25 degrees Celsius, but if that temperature changed, the Ka would change, but we don't deal with questions like that at this level. So you can find like pictures of Kas all over the internet, all over examples, but you can see them all here. So remember, your strong acids won't have a Ka because they completely dissociate. You'll only have a Ka for your weak acids because they partially dissociate and are in equilibrium. And if we compare the Ka value, you can kind of see which ones are actually stronger weak acids than others. And what I mean by a stronger weak acid is a weak acid that dissociates more, so has a larger Ka. Because if it dissociates more, there are more ions, so there's more H3O+. So it's quite an awesome little thing. And what you'll see here is hydrofluoric acid is a stronger weak acid than acetic acid. Acetic acid is the old-fashioned name for ethanoic acid, by the way. We don't actually refer to acetic acid. Well, I don't use acetic acid, I use ethanoic acid, but it's the same thing. And you can see here that because hydrofluoric's Ka is actually larger, this means more of it dissociates, and so there will be a higher concentration of H3O+ in the same concentration solution, which means that hydrofluoric acid would be a stronger weak acid than ethanoic acid. They're both weak acids, but you can actually compare the strength of those weak acids according to the Ka and how much it dissociates. So for a weak base, it's a Kb, and again, weak bases partially dissociate. Most of them remain intact, very few ions. And you can see I've made up these values again just to show you that if you've got a 0.1 molar concentration of NH3, you've got very few ions in your solution. So I've just made them up. We can write our equilibrium constant by doing products divided by reactants and ignoring the liquid water, and that's its Kb. And we can look these up on the internet, resource booklets, and just remember that will change if the temperature changes. So remembering what a Ka and Kb mean, the whole thing is that it's a mathematical relationship between the concentration of the products and the concentration of the reactants. A large Ka or B means there's a higher concentration of products, which means there are more ions and you'd get a stronger acid or a stronger base. A smaller Ka or B means there's a higher concentration of reactants and you'd have very few ions in the solution, so it would be a weaker weak acid or a weaker weak base. So just a wee summary here, that a large Ka, the stronger the acid, as more of it dissociates. And the larger the Kb, the more base dissociates, the stronger the weak base. So a large Ka, Kb means the stronger the weak acid or base. A small Ka, Kb, the weaker the weak acid or base. So here's a wee task for you to write Ka, Kb expressions for the following. So let's go through and do this. So first of all, you need to do equations, okay? So aqueous plus H2O liquid goes to CH3, NH3 plus aqueous, and OH minus aqueous. And then we do products divided by reactants. It's a base, so it's called Kb. So it's going to be CH3, NH3 plus divided by OH minus divided by CH3, NH2. So now we've got methanoic acid, so HCOOH aqueous plus H2O. We just say all the weak acids and bases are aqueous, by the way. Liquid goes to HCOO minus, which is methanoate ions, and H3O plus. So we do products divided by reactants. This time it's a Ka, so it's HCOO minus, H3OO plus, OO plus, O plus, and HCOO. Hopefully you get that. This last one, bit of a trick. Trying to be mean here. KOH is a strong acid or base, so it completely breaks up into ions. Remembering, because it's a strong base, it doesn't have the addition of water, because strong bases are solids, and there will not be a Kb expression for this because it's a strong base. It is not an equilibrium. So that was a bit mean of me. Okay, so conjugates of acid-base pairs. Now, we've been through this in the standard level stuff, but it is just so important. Conjugate acids that are made from weak bases are weakly acidic. Okay, so here's your weak base. The conjugate acid ammonium is weakly acidic. Okay, and that means that if that ammonium ion will then react with water to a small extent, but still react with water and produce hydronium ions, which is why it's weakly acidic. Now, the conjugate base from a weak acid are weakly basic. So methanoic acid, its conjugate base is methanoate. Methanoate ions are weakly basic, meaning that they can further react with water to produce hydroxide ions. And you'll notice that they reproduce what they were made from, okay, and that's how it works. And it's a really huge property of these substances, and it's going to make a heap more sense when we start talking about salts, and the fact that if you have a salt that contains this ion, it'll be basic, and a salt that contains this ion, it'll be acidic. And remember, your conjugates of your strong acids and bases are neutral, so they don't have this property. So this is unique to weak acids and bases. So here are 3 questions that I'd like you to do. So please pause your video, give them a wee go, and we'll continue on. Okay, if I can get the slide to change.